Hey, so today we're going to be talking through Module 5, Lecture 1. And as usual, whenever we get close to the actual assignment, I'll, kind of do some run through. So this is just an introduction to correlation and simple linear regression. So you've probably heard of regression before, I would think, but imagine, right, two things that are known to be related. Imagine we want to look at, so you've been making scatter plots for a while. So imagine you want to look at how weight is predicted by height. So if you get taller, you have more room to carry more weight, I guess. Tend to be that taller people weigh more. So you might get a scatter plot, and the scatter plot might look like this, for example, something like that. And the goal is you want to kind of fit a line to this data. So you probably remember back from algebra, right? You have like y equals mx plus b. So this would be y, this is x, and this line would be y equals mx plus b. Basically, we do the exact same thing in this, only you find the mx, you estimate it. So just like how, right, we got estimated proportions for like the percent of people that had a heart disease, or we got estimated means and things like that. We're going to get an estimated slope and an estimated intercept based on our data. And that slope and that intercept is supposed to be set up to where we have the minimum squared distance between each of the data points in the line. So, you could imagine, right, if I made a line like this instead, this line right here, I'd be close to these points up here, but I wouldn't be as close to these points down here. So the regression line that's produced here is the one that, on average, across all the data points, is the closest to the data. All right, so that's the general idea. This is going all the way back to algebra. I know that y'all have talked about this for sure in high school. And all we're doing is we're using data to estimate these things, just like we've been doing the whole time. So let's start with some notation. Consider two continuous samples of data from the same observation. So in that example, right, I have a person's height and a person's weight. So me, I'll go put in, I'm 5'11" and I weigh 220 pounds. So I put that into, that would be my data point. And everybody in this class would have a data point, and whoever is enrolled in the study would all have data points. The way we're going to notate it is in pairs, right? So x1 would be my height, y1 would be my weight, x2 would be somebody else's height, x2 would be y2 would be somebody else's weight, all the way up to xn. And these are continuous, and they come from the same patient observation. So they're not binary, like yes, no. They've got to be some kind of like numerical data point, like age or BMI or something like that. Examples. I don't know why I repeated this example 3 times, but xi could be the temperature today. How old is the temperature today? Predict the temperature tomorrow. It probably does a pretty good job, considering, right, that if today we're in the summer, tomorrow we're going to be in the summer too. So correlation is probably something you've heard a lot about. You've probably heard correlation doesn't imply causation, that kind of statement. And correlation is still, I want to talk about it in terms of that line. It still is represented through that line. That's still what's going on at kind of the base sense. But this gives you a numerical summary of how related two variables are. So correlation is something we call rho. It's a population parameter, just like mu and pi and things like that we've looked into. Rho must be between -1 and 1. Here, a -1 means that if rho is -1, I'll just show like this, rho is equal to 1. And the line that we have looks like this. It's like in the positive direction. If rho equals -1, it's in the negative direction. And if rho equals 0, then basically what we have is just a straight line. So as x changes, y doesn't change. And that's how to think about this parameter here. So again, if x increases, does y increase? If x increases, does y decrease? If x increases, does y stay the same? If it stays the same, then that indicates no correlation, so 0 correlation. So here, negative correlation doesn't necessarily mean that variables are not correlated. It just means that they're correlated in a negative direction. Increasing one value decreases the other. If they're positively correlated, increasing one value increases the other. So as an example, right, talking about height and weight, Increasing height typically increases your weight. Increasing caloric intake typically increases your weight. Increasing your exercise amount per week typically decreases your weight. So a negative correlation. Now, obviously, there's lots of other factors that go into it that we'll talk about in the next module. So that's kind of looking at multiple factors in relation to one outcome. So does exercise predict weight? Does what you eat per day predict weight? Does sleep patterns? All those kind of things together, how do they work? But here in a kind of the simple perspective, I have one variable, I want to predict another one. So again, correlation of 0 implies no correlation, and also independence. So independence, right, we talked about from a categorical perspective. Independence would mean that the probability of being in any category for a categorical variable within a row of another categorical variable doesn't depend on that row. Correlation near 1 implies strong positive. Correlation -1 implies strong negative correlation. So here's the formula. Again, you're not going to have to use this. You're just going to use R to do it. But I just want to give you kind of some intuition on why this is something that we use. X bar and Y bar, that's the sample means for the two continuous variables. You can estimate this proportion here like this. So it would be the sum of all the Xi's minus X bar times all the Yi's minus Y bar over the sum of squares multiplied together on the bottom. So just as kind of a intuition, this formula on the bottom for X and Y, they're missing a factor, like a N factor here. But these formulas on the bottom, these are essentially the variance. So the variance of your X data, the variance of your Y data. This formula on the top is essentially called the covariance here. How do these vary together at each data point around the respective means? I definitely challenge you to do this in R. You totally can do this. You have a vector X, you have a vector Y, you can take the means. You can subtract the means from the vectors, multiply them together and sum them. You can do the same thing on the bottom and square those values. We want to test if height and weight are correlated for Louisiana males. So again, correlation indicates the strength of a linear relationship between two variables. So it could be, right, a nonlinear type thing. You should still kind of see a linear relationship. Like if reality, if in reality, the true relationship looks something like this, and you fit a regression line, then what you might see is you might see a line like this, or if you have lots of data on both sides of this, it might kind of fit a line through it. So there can be nonlinear relationships that you might miss. There's tricks around that. You can add polynomial terms into your regressions. We're not getting into that in this class. Just know that there are solutions for this. And this is not to give you, right, an expertise in statistics. In fact, I don't recommend, especially if you're doing if you're working for any kind of a large company or you're doing any kind of major policy decision making, I do not recommend doing your own statistics unless it's very kind of simple. I recommend at the very least consulting with the statistician. We're trained. I have, 4 years college. I did a 2 years master's and I did a 4 years PhD. So I have 10 years of training in statistics, and most statisticians are the same way. So when you can rely on us, what this class is supposed to do is to introduce you to some basic things and also give you maybe a little understanding of what's being reported in the literature. Okay, so I can test this null hypothesis, rho is equal to 0. What does that mean? If rho is equal to 0, X and Y are independent. And this hypothesis test assumes that Yi minus Xi has normally distributed a normal distribution, which may or may not be true. So as an example, I don't have it in here, but you're actually going to use core.test here. So the syntax is, if I've got X and Y, the syntax is core.test X, Y, and that's going to give the output that we have below. So I'm going to talk about how to read it. So this is the output. It's an example where I've got height and weight, and I use core.test. I get a small p-value. This p-value, again, is testing whether there's no relationship. we reject the null. So there's clearly some kind of linear relationship. And you can see that here, right? Here's the estimated regression line that I add to it. This is my estimated correlation down at the bottom, 0.89. And I also get a confidence interval for this correlation. Again, if this confidence interval overlapped with 0, that would mean I would not reject this null. And just like I've done before, I can test if I want to, H naught, rho greater than or equal to 0. I can test rho is equal to different values. I can do all those sorts of things. So here's the core dot test, right? I can do alternative equals greater. You can see here, I can do two-sided, greater or less. I should be able to pick a value, I think. I don't see where it is. I should be able to pick a value here. This is really going to be important for you, this method. So these methods, Pearson is the one that assumes normality. So it's a parametric test. It's more suited, I think, for larger sample sizes. Kindle is a non-parametric test. It's very conservative. And Spearman is also a non-parametric test. So if you have a small data set, I recommend usually using method equals Kindle. If you have a larger data set, Pearson is fine. Okay, so here's an example. Recall the data set where we have before and after blood pressure example in cancer patients who may or may not have received aspirin. Are the first and the second blood pressure correlated? That's what we want to know. And we can test the null. Is the correlation equal to 0? So I have my blood pressures. Remember, this is what the data looks like. This is me reading it in. Here I've read in the data. I'm looking at the data. And remember, this is from module 3, lecture 1. And here are my 2 data points. And I'm just going to do core.test. I'm going to grab the data blood pressure 1, data blood pressure 2. And then I get my test. Here my p-value is pretty large. My estimated correlation is negative, but it's also very small. So it's like close to 0. And you can see my confidence interval also overlaps with 0. So here I don't reject independence. I can't say that blood pressure 1 and 2 are not independent anymore. So I don't reject the null here. And conclude that there's a relationship between the 2 blood pressures. And you can see that on a plot. So I just plotted these 2 together. I did a title, an X label, and a Y label. You can see that here. Okay, what about an association between the first blood pressure and the change in blood pressure? Why? Why do I think that we might see that? Is because a couple of classes ago, right, we looked at initial blood pressure groups, so whether they were, between different values. And we saw that they had significantly different changes in blood pressure, overall change in blood pressure using ANOVA. Now I'm just going to plot these together. So this is BP diff again, blood pressure 2 minus blood pressure 1. So I'm creating this variable. And again, I'm using this $sign so that now it's an actual variable in my data set that I can index. And I'm plotting the blood pressure as a function of the BP diff. And you can actually see, right, there's definitely this negative decreasing trend here in the change in blood pressure. So that basically means the higher your blood pressure is initially, the more likely you are to lose more blood pressure over time. And that kind of makes sense. If you're elevated, how much higher can you go without dying? And then I do a correlation test. I have the correlation test values here. So again, this is testing. You can see the alternative here. True correlation is not equal to 0, which means my alternative here, if my alternative is rho not equal to 0, then that means that my null is rho equals to 0. And you can do the same thing with greater or less or however you want to do it. This is my 95% confidence interval. It's definitely very negative. Again, the biggest this thing can be is -1. So this thing is fairly close to -1. Okay, so again, I started out kind of showing you graphically simple linear regression. Correlation is doing pretty much the exact same thing as simple linear regression, at least the one that does ANOVA or the one that assumes normality. The non-parametric test is a little bit different from this, but essentially all these correlations are drawing a line and then kind of measuring the magnitude of the line. So there's no way to draw a line where everything fits exactly, but we can fit the general trend with some errors. So we set up this statistical model here. So I just want to point out and try to explain what this is. So I'm assuming that my Y data can be modeled based on, this is some intercept coefficient, this is my B, and this is a slope coefficient, this is my X data, and then some error term. So effectively what I'm saying is, hey, look, I've got these two unknown parameters, beta 0 and beta 1. I don't know what they are, but I'm going to use the data to estimate them. So if I get a new data set, I'm going to get a new estimated beta 0, new estimated beta 1. And I'm assuming that I have some errors because I'm not going to be able to fit everything exactly likely. The world is just not deterministic like that. And it's assumed that the errors here are normal with mean 0 and a variance sigma squared. And we actually estimate sigma squared as well. So based on the spread of the data around the general trend line. So just think about the interpretation. If beta 1 is bigger than 0, that indicates that as xi increases, so does yi. Vice versa, right? If it's less than 0, as xi increases, yi decreases. I'm going to use the data to estimate beta 0 and beta 1. These estimated values, I'm going to call them hats, beta 0 hat and beta 1 hat, which we've been doing this all along, right? We got pi hats, which is a p if you use prop dot test. You get a hat for a mu, which is the average if you do a t-test. You get a pseudo median if you use a Wilcox test, which is an estimate of the true population median. We've been doing this all along. So this is just a different context. We're assuming this model, we're assuming our data looks like this. So probabilistically, mathematically, our data looks like this. And then we actually use the data itself, whatever we observe, to estimate these parameters. And again, how are they estimated? Basically, I am just subtracting off the predicted means or the predicted value for y from the real value of y, squaring that difference, and then adding all of them up. So I'm trying to minimize the squared distance between each real point and the line. And here I can test if there's a relationship between x and y by testing the null beta 1 equals 0, which means if beta 1 equals 0, then that means as x increases, y doesn't change, right? Y doesn't change if that happens, versus h1 beta 1 not equal to 0. So this test is actually the same thing as testing if rho is equal to 0. Okay, so here I'm going to use this function LM. So LM here has a formulaic function in the same way. Here I have calling an object M1 equals LM. So M1 is just going to have my linear regression. LM, I'm doing blood pressure difference. And then I do that little tilde, the formula here, to blood pressure. This is my M1 data. You can see these are my estimated coefficients. So my estimated beta 0 here is 163, and my estimated beta 1 is -1. So this is not equal to 0, right? But is the p-value, is it significantly different from 0? So whenever I actually do a summary of this object, I get all of that information that I want. So I get the estimates here, I get these standard errors, I get this t-value here, and then I get these p-values. I really care about these p-values. So this p-value here is testing whether beta 1 equals 0, and it's significant. So again, 2e to the -16, that is 16 zeros, 0.000000016 times, and then a value. So that's so much smaller than 0.05. So I reject the null that beta 1 equals equal to 0, which means that there is a relationship between initial blood pressure and the change in blood pressure over time. Similarly, this intercept is significant, which means that basically there is some kind of like, non-zero effect. And you can see that, right? If this had more of a zero effect, it would be more centered around the line than anything. So again, yeah, this is our estimated slope. This is my p-value, and this is actually testing the null beta 1 equals 0. Sorry about that mistake. Here I have this adjusted r squared. This adjusted r squared, don't worry about it right now, but it's important in multiple linear regression. So again, right, since the beta 1 hat is negative, that indicates as x increases, y decreases. So what's nice about this object too is I can actually draw a line really easy, just using this function AB line. Why is it called AB line? It's called AB line because AB line assumes that your data looks like this. And so if I feed in a linear regression, which actually has this form, it'll just plot the line for me, which is really nice. And you can see that line. Here's my estimated regression line. Okay, non-parametric association. So this is all assuming, right, a linear model. So it's got to increase in a line, can increase like in steps, can increase, you know, in a quadratic form path. All of the things we talked about assume two things. Number one is errors are normal. And what does that mean? That means that, you know, if I have this predicted line, I'm looking for something where they're kind of equally spread around the data. What I'm not looking for is something that looks like this. So where I have, you know, like this huge skew up at the top, and then maybe I have like a small skew down here. So that's clearly not normal. Remember, normal looks like this bell-shaped curve, you know, bell-shaped curve. The second assumption here too is that the X-Y relationship can be modeled with a straight line. And that might not be true, right? If I have data that looks like, again, looks like this, you know, then maybe I don't really have a linear relationship. Maybe it's quadratic. So again, there's ways to fix this in the settings we talked about, but one easy way is just doing a non-parametric method. So again, Pearson's correlations assumes it's normally distributed and there's a linear relationship. So it might not pick up nonlinear associations. And when your data is not normal, the hypothesis test behaves poorly. So the easiest solution is Kendall's tau. And that's an easy change to do that. All you need to actually do is come into your correlation test function and change method to Kendall here. So tau here is this association. It's a monotonic association. It's not necessarily a linear association. And again, it's also between -1 and 1. So here I get an estimated tau. It's like kind of a non-linear increase, decrease. It's kind of the same thing, but it's not like a line. So Kendall's tau could do things like, Kendall's tau could handle, you know, things like this. Like if they just kind of step, it wasn't really a line so much. Or, you know, it starts up here and then it goes down, then it goes way down and it's a line, something like that. Kendall's tau would pick this up, whereas a straight line might not. So here I get this p-value. It's very significant, which means that there is a significant association between X and Y. And since this association is negative, that means as X increases, Y tends to decrease. Maybe not linearly, but tends to decrease. And that's it. So my sort of suggestion on those two tests is if you have a small data set, like the rule of thumb is 30 for using parametric tests. I think that's fairly agreeable. But if you have a small data set, like 15, 20 observations, use Kendall tau, method equals Kendall. If you have more than that, you can use standard correlation. And that's it for today.